Good afternoon, students. This is the 10th video of thermodynamics. We already discussed the work done in adiabatic process of reversible expansion, and from this work done, we already derived the work done. The work done that we get from the adiabatic process is equal to minus 1 by minus gamma plus 1, then r t2 minus r t1, and in this case if you take r as the constant and outside w is equal to minus r by minus gamma plus 1 t2 minus t1, that we already discussed. I would also derive this work done. And in some cases there are some relationships is there in adiabatic process. If some value is not given to you, then how this value you can derive, and from this how you know that? Suppose we know that p1 v1 to the power gamma, p2 v2 to the power gamma. If gamma is equal to 1, it becomes ideal, yes. That means p1 v1 is equal to p2 v2 according to the Boyle's law. We also get the same Boyle's law. Okay, so in that case how you know that? Now p1 by p2, take this p2 to this side, is equal to v2 by v1 to the power gamma, and this is the relationship of pv. This is the relationship of PV relation, PV relation. Then from you can also derive other relation, pressure, temperature and volume temperature. Just you know that from the ideal gas equation it is also known that PV, P1 V1 is equal to RT1. I want to replace this pressure P1, then whatever you want you have to put here, whatever, not here, you have to put here. Then P1 is equal to RT1 by V1. Okay, so in this place of P1 I put this value. Similarly I know P2 V2 is equal to RT2, then your P2 is equal to RT2 by V2. Now take this P1 to this side and this P2 to this side. Then substituting this value, what you know? Now suppose in place of P1 I write this one is equal to RT1 by V1 to the power gamma. In place of P2 I write this value RT2 by V2, then V2 to the power gamma. You see here that it V1 to the power 1, V1 to the power gamma. That means when you take this one to the above side, it is gamma minus 1, and these are also constant, cancelled. So now becomes T1 V1 gamma minus 1, nothing means it is 1. That's when it will go up, it becomes minus 1. It is V1 to the power gamma, V1 to the power 1. When it go up, V1 to the power gamma minus 1. Okay, because base is same, so it will be same thing happen in this case also. Here is T2, nothing means V2 to the power 1. V2 to the power gamma, so base is same, so this gamma 1 will go up, becomes minus 1, that means V2 gamma minus 1. Then what happens? Now we can write that T1 by T2, take this one to this side, V2 by V1 to the power gamma minus 1. This is the temperature volume relation. This is temperature volume relation. We derived pressure volume relation. This is the temperature volume relation. Now pressure volume relation over, temperature volume relation over. Then I want to get pressure temperature relation. In the same formula we have to put, since we know that P1 V1 is equal to RT1. So V1 is equal to RT1 by P1. Now I substitute this V1 in this point. Similarly, you take P2 V2 is equal to RT2. Then V2 is equal to RT2 by P2. Now substitute this V2 in this point. Then what you get? Now P1 in place of V1 I write this one is equal to RT1 by P1 to the power gamma is equal to P2, and in place of V2 I put this value RT2 by P2 to the power gamma. Now what you do? Now you separate, you split this one. Then it is P1, then R to the power gamma, T1 to the power gamma divided P1 to the power gamma. No problem. In this case also P2 R to the power gamma, T2 to the power gamma, then P2 to the power gamma. No problem. Here you see it is base P1, it is just both base is same. So here it is 1, here it will be gamma. So when you go up minus gamma, then it becomes P1 1 minus gamma, then R to the power gamma, T1 to the power gamma. In this case also P2 1 gamma, when go up minus gamma, it becomes P2 1 minus gamma, R to the power gamma, T2 to the power gamma. This one cancel, both sides is same. So then what happens? Take pressure in one side, temperature in another side. Take pressure in one side and temperature in another side. Then what you get? P1 by P2 to the power 1 minus gamma, T2 by T1 to the power gamma. Okay, this is the relation of pressure temperature. This is the relation. This is the relation of pressure and temperature. Remember, these are all adiabatic process. This is the adiabatic relationship. It is not ideal relationship. It is the adiabatic relationship. So you know that how the pressure volume, temperature volume, volume temperature relationship we derived. Similarly, we derived the work expression for work W. Similarly, we derive expression for U. Expression for U means in the two way you can derive it from the first law of thermodynamics. From the first law of thermodynamics. From the first law of thermodynamics, del Q is equal to du. Here we can write here, suppose this is the first law W, then du is equal to del Q minus W. Then here you see that work, you can put the formula of work done, this formula in this point. You can put this formula in this point, or you can write minus PdV. It minus means expansion. In this case, del Q is equal to 0 because adiabatic process. Because adiabatic process means the process in which heat cannot exchange between the system and the surrounding, but work can be exchanged. Work can be exchanged, but heat cannot exchange. As heat cannot exchange, del Q is equal to 0. That means in adiabatic process, for adiabatic process, del Q is equal to 0. Then what you get? Now you get du minus PdV. Okay, that is the work done. Either you get this formula, that means it is equal to minus PdV. Whether you get this formula, or you can derive in alternative way also. देखा जाउछि. Then in this way, then in the on another way also we can derive. We know that Cv is equal to du by dt, constant volume. This is also we know. Then we can write that du is equal to Cv dt. This is also the another relationship. It is for 1 mole for n mole of gas, because Cv is considered as molar heat capacity at constant volume. Molar heat capacity means 1 mole of gas. For n mole of gas, you can write that du is equal to n Cv dt, or temperature change you can write that n Cv T2 minus T1. In this way also you can derive the relationship. Okay, then expression for Q. Expression for Q means it is equal to 0 because it is heat adiabatic process. That means here Q is equal to 0 because it is adiabatic process. So there is no heat exchange between the system and surrounding. So only work can exchange, but heat cannot exchange. So Q is equal to 0 for adiabatic process. Then expression for H. Expression for H. We know that same process also we can carry out. Cp is equal to dH by dt at constant pressure. Then dH is equal to Cp dt, or you can write that dH is equal to Cp T2 minus T1. This is for 1 mole. For n mole you can write Cp T2 minus T1. In this way, if the value is given to you, then you can put this value in this equation. Otherwise, enthalpy can be also expressed in zero form. Zero means how you express. Now we know that dH is equal to du minus w. That means expansion of work done carried out. Du is equal to, we know that du is equal to Ncb T2 minus T1, and Ncp T2 minus T1. So w is equal to minus Vdv. So in that way also you can do this expression for the enthalpy, but you can remember this one is better, and this one for du and this one for dH. So any mole you can calculate from this point of view. Okay, this is the reversible process. Now second one is adiabatic irreversible expansion of ideal gas. Adiabatic irreversible expansion of ideal gas. Adiabatic irreversible expansion of ideal gas. You also derive dt in terms of temperature, because ideal gas internal energy is a function of temperature, and dt is equal to 0, then du is equal to 0. In that way also you can find out, no problem. Okay, then first is expression for w. You have to see that what value is given to you. Expression for w. Expression for W. It is adiabatic, heat exchange is 0, irreversible, that means whatever you do in nature, it all are irreversible process. Expansion from lower volume to the higher volume, that means expansion means suppose this is my initial volume V1, it is expand to this one is V2, then this to this is V2 minus V1. This is the expansion. Then expression how you carry out. Now W is equal to minus P external V2 minus V1. This is the PdV. What done is equal to minus means expansion. What done by the system. In place of V also, suppose volume V is not given to you. Then from the ideal gas you can substitute this value V. We know that P2 V2 is equal to RT2. Then V2 is equal to RT2 by P2. So in place of V2 I can substitute this one. Similarly P1 V1 is equal to RT1. Then your V1 is equal to RT1 by P1. Now in place of V1 I substitute this value. Now your W becomes, you see what value is given to you. In this way you have to proceed. V2, instead of V2 I write RT2 by P2, minus instead of V1 I write RT1 P1. Okay, then you take the LCM. W is equal to minus P external, then LCM is P1 P2. We get what? P1 RT2 minus P2 RT1. Okay, this is in the bracket. Now your W becomes, here you take R common, no problem. If you take R common, then what is the expression for W? W is equal to minus P external, take R common, we get P1 T2 minus P2 T1 divided by P1 P2. This is the expression for work done. You see that what value is given to you. In this way also you proceed. In the previous cases also, in isothermal cases also, irreversible, we put this value. This is the formula. But if the volume is not given to you, then you substitute this value. In this process also you do this one and you will get this value. This is the expression for W, for irreversible process. Okay, you see that what value is given to you. In this way you have to proceed. Then expression for U, the same way we derive reversibly expression for U. We know that Cv is equal to du by dt at constant volume. This is for ideal gas we derived. Then du is equal to Cv dt. Then we can write Cv T2 minus T1. For n mole of gas, du is equal to NCV T2 minus T1, where Cv is the molar heat capacity. Molar heat capacity. Molar heat means for 1 mole of gas. For n mole of gas you can write in this way. Or if you want to derive if there is no temperature change, that means dt is equal to 0, because in ideal gas internal energy is a function of temperature. Whatever we do in ideal gas. In ideal gas, internal energy is a function of temperature. So when dt is equal to 0, then du also equal to 0. If there is no temperature change, if he is giving you in isothermally, then dt is equal to 0, or temperature is not changed, then du is equal to 0, because in ideal gas internal energy is a function of temperature. So dt is equal to 0. In this case also, previous case also, if temperature is not changed, because ideal gas is a function of temperature, dt is equal to 0, then du is also equal to 0. Okay, you see that what value is given to you, and in that way you have to proceed. So du is equal to NCB T2 minus T1. Okay, in this way you can derive the du. Then expression for Q. Expression for Q means in case of expression for Q. In expression for Q you see that Q is equal to 0. Del Q is equal to 0, because heat will not change. Heat exchange is not possible because it is adiabatic process. Adiabatic process. That means heat cannot exchange between the system and the surrounding. So heat delta Q is equal to 0. Then expression, when delta Q is equal to 0, that means expression for Q. Then expression for H. Expression for H. H is equal to, we know that Cp is equal to dH by dt at constant pressure. So dH is equal to Cp dt, or we can write that dH is equal to Cp T2 minus T1. Then for n mole, NCp T2 minus T1, where Cp is the molar heat capacity. Molar heat capacity at constant pressure. At constant pressure. That is the molar heat capacity at constant volume. At constant volume Cv, here P, pressure constant. So in this is the enthalpy expression for enthalpy. So this is the adiabatic irreversible expansion of ideal gas. Then adiabatic free expansion. Adiabatic free expansion. Adiabatic free expansion of ideal gas. Adiabatic free expansion of ideal gas. Expression for W. Expression for W. How we express the W? In expression of W, that means it is free expansion. Free expansion means we know that work done is equal to minus P external dV, or minus P external V2 minus V1. In free expansion or vacuum, P external is equal to 0. P external is equal to 0. So W is equal to minus 0 into V2 minus V1. 0 to something means 0. So W is equal to 0 for free expansion, adiabatic free expansion. Same thing happen also in isothermal cases. In isothermal cases also, vacuum external pressure 0, W is equal to 0 in free expansion. So in adiabatic expansion, free expansion, vacuum is equal to 0, vacuum means external pressure is equal to 0, so W is equal to 0. Then expression for U, expression for U, expression for U, expression for U, expression for U means you also can like tells like this in this process also, as in case of ideal gas, in case of ideal gas, internal energy is a function of temperature. So at dT is equal to 0, du is also equal to 0. At dt is equal to 0, du is equal to 0. dt is no temperature change, then du is equal to 0. Or you can also write like this is from the first law of thermodynamics, from the first law of thermodynamics, from the first law of thermodynamics, we know that del Q is equal to du minus W, then plus W, this is the first law. That means when du is equal to del Q minus W, minus means here is the expansion were done by the system. You cannot put here plus. If you write plus here means were done on the system. Now in adiabatic process, del Q is equal to 0. In adiabatic process, del Q is equal to 0. Del Q is equal to 0 in adiabatic process. As it is adiabatic process, del Q is equal to 0. Then du is equal to del Q is equal to 0. Work done also 0, so is equal to 0. So du is also equal to 0. That means du is equal to 0. We see that W is equal to 0, du is equal to also 0. Expression for Q, expression for Q, as it is adiabatic process, del Q is equal to 0. As it is adiabatic process, it is adiabatic process, so del Q is equal to 0. As it is adiabatic process, del Q is equal to 0. Then expression for H, expression for H. In expression for H, we know that dH is equal to du plus W, PdV. That we know. PdV means work done. That means it is equal to dH is equal to du minus W, because minus means expansion work done by the system. Then what is the value? Du is equal to 0, W is equal to 0, so dH is also equal to 0. So that means in case of free expansion, in case of free expansion, in case of free expansion, W del in case of expansion, W is equal to du is equal to dq is equal to dh is equal to 0. Everything is 0 in case of free expansion. That means in case of free expansion, no pressure volume work is possible because external pressure is 0. Similarly, internal energy is a function of temperature in case of ideal gas. So ideal gas, the temperature is equal to 0, so du is equal to 0. In adiabatic process, del Q is equal to 0 because there is no heat exchange between the system and the surrounding, but work can exchange. And dH is also equal to 0 because dH is equal to du plus PdV. PdV means work done. Du is equal to 0 and work done is equal to 0. So delta U is equal to 0. dH is also equal to 0. So in this is the adiabatical pre-expansion, just like the isothermal expansion of ideal gas, everything is 0. In this case also, adiabatic process of ideal gas, is also equal to 0. That means in free expansion neither work done nor heat exchange nor internal energy nor enthalpy is carried out. Then next step we will go adiabatic reversible expansion, adiabatic reversible expansion of van der Waals gas. Here we consider van der Waals. Ideal gas is over. So in the van der Waals gas, expression for Q and W. Expression for Q and W. From the first law of thermodynamics, from the first law of thermodynamics, for the expansion of gas, what is formula? Now del Q is equal to del U minus W. Del Q is equal to del U minus W. We know that for adiabatic process, adiabatic reversible expansion, for adiabatic process del Q is equal to 0, but heat cannot exchange. That means dQ is equal to 0 is equal to du minus W. That means du is equal to W. That means whatever the value of change in internal energy, that was also the work done. If you find out the internal energy, then that was the same formula is used for the work done. Then in the next class we have to in the next video we will tell you expression for delta U, because it is already it will be more data. In the next class we will express you expression for internal energy U. When you see the expression for internal energy, then you can find out the same formula used for W. Okay, you will go through this video. If you have any doubt, you can ask. Sometimes I cannot pick up your phone because a lot of work is carried out in our college. Some are sending something else. So you just WhatsApp me. If you have any doubt, just WhatsApp me instead of calling. If you just miss call me, then I will call you when my time is available. Okay, no problem. पढ़ापढ़ी करिबो, जमा बुलाबुली करिबनी, कारण तुम तो जानिछ सब जा काली सेकेंड ईयर रे गोटे पिला को बाघ नहीं पळैछि आ साडी छाड़ी के दिगला तुम ता ना जानि परिबनी, तुम ता संगे मिसुन, तेनु से पिलाटा को नहीं बाघ पळैथिला ताको आनी छाड़ीला, ता ना होछि अभिमन्यु। तुम चिन्हि न ताको, से ता बाघ नहीं पड़ीथिला, पढु नथिला, से टीवी देखुथिला, तेणु बाघ धरिकी पळैला। सब गाँ तो बाघ सिंह छड़ाई, गवर्नमेंट छाड़ी, गोटे बांगे 4, 5, 6 एमती गोटे जगह तो 7टा बाघ छड़ाई, सिंह भी छड़ाई। तेणु से खाऊना, छेली फेली कि मेढ़ा खाइबे, खाली मनीष खाइबे, से 2-3 दिन है खाई ना। तेणु तुम बाहर बुलबनी कि टीवी देखनी, खाली खाता बही धरी पढ़। टीवी भी देखिले जदि सिंह देखला कि बाघ देखला धरिकी पलैब, छाड़बनी। काली गोटे सेकेंड ईयर पिला को बाघ धरी पलैथिला, खाली कहला भूल मागिला, भूल मागिकी कहला मैं पढ़ी बोली, से छाड़ी दे गला घरे, ना खाई था। से पाठ पढ़िया पिला को खाएनी, पाठ न पढ़ले से खाईदेव। तेणु हुशियार रढ़ापढ़ी कर, बाहर को जमा आसबनी कि टीवी भी देखनी, खाली खाता बही से पढ़। जहाँ डाउट थी व्हाट्सएप पचार ना मिस कॉल करदेव, मोर टाइम हम मु तुमको रिकॉल करी कहीदेवी। ओके, गुड आफ्टरनून, थैंक यू वेरी मच।